Alright, we're going to review two practical approaches for internal flows. So just as a quick reminder, this is the equation compared to the previous video or the other. I added the possibility of having a pump, and this is the friction loss equation, so please remember that, and the friction loss equation is given to you by the Moody diagram. This is again a slide from the other video, and this is what really we're interested in. The simplest case is when the flow rate is given, but you're looking for the pressure difference between point A and point B. Since the flow rate is given, you know you can calculate exactly your Reynolds number, and that's equal to Vd over nu. From the Reynolds number, obviously, you can calculate your friction losses, and from the knowledge of the bulk velocity, you can calculate your minor losses as well. And now, everything on the right hand side is known in this equation, and you calculate PA minus PB. So this again is the simplest case. Now for a slightly more complex case, what happens when you know delta P, so PA minus PB, but you don't know the flow rate? And that's a problem, because how are you going to identify or calculate your Reynolds number? So that's PA minus PB. So the best way to do it, to estimate your Reynolds number, is to use Bernoulli. Then from the knowledge of the bulk velocity estimated by Bernoulli, you can estimate your friction loss. And you solve for this equation, where now this part is estimated, and this part is known. Hopefully you know everything here, but for the exam you'll definitely know everything here. Now you can calculate the new V, the new bulk velocity, and from this new V you're going to calculate a new Reynolds number, a new bulk velocity, and a new friction factor. And you iterate 3 to 5 until convergence. So let's see a quick example. We're going to look at the discharge of a large tank. The tank has a constant water level of 1 meter above the opening, and is maintained by this. The pipe is a steel pipe with a given roughness, and there is a square entrance at the pipe and opening onto an infinite domain at the bottom of the pipe. So what assumptions are relevant here? Steady flow, large tank. So what does that mean? That means that if I choose the upper interface, water interface, to be A, that means that BA is equal to 0. Also, I have PA is equal to PB. PA is the pressure atmospheric, and Y is the pressure at B, which is the exit pressure, the atmospheric pressure. Well, because your jet here, the outside of your jet, is at atmospheric pressure, and you could show using the Navier-Stokes equation that the distribution of pressure is pretty much uniform inside the jet. So therefore, the pressure at B is the atmospheric pressure, and also PA. Okay, so what else? Roughness, epsilon over d. We're going to need that parameter, and that's 0.00 0.045. So let's remember this. The fact that we have a square entrance, so give us an idea of the minor losses or the coefficients. So minor losses, entrance, if you look up in your book, for the entrance, square entrance, k equals 0.5, so we're going to call that k in, and exit, k out, is equal to 1. That's the standard when you have an exit to an infinite domain. Alright, so we have pretty much everything we need. So if we apply Bernoulli from point A to B, again, this is A and this is B. So if we apply that across a streamline, what we have PA is equal to PB, so those go away. We have the velocity is negligible at the interface, so we end up with the typical Torricelli equation, which is V is equal to the square root of 2g ZA minus ZB, square root of that, which is equal to 2 times 981 times 9 meters, and the square root of this, and that's 13 meter per second. My Reynolds number RD is equal to 13 times 0.1 divided by 10 to the power minus 6, so that's 1.3 10 to the 6. So now I jump to my Moody diagram, and in my Moody diagram 1.3 10 to the minus 6 is going to be roughly here, and my epsilon over d is 0.04, so I follow all the way, and this is here 0.04, which means that I am roughly here at 1.65. So using f is equal to 0.0165, now I have ZA minus ZB is equal to V square over 2G. Alpha B, well, the Reynolds number is very high, so we can safely say that it's turbulent, or at least from the estimated velocity, plus we have only one friction loss, so that 0.0165 times 8, sorry, over 0.1 plus 0.5 minor loss for the entrance plus 1 minor loss for the exit, and with all of this you get V is equal to 6.79 meter per second, which gives you a corrected Reynolds number now is equal to half about what we had before, 6.8 10 to the power 5. So now I need to jump to my Moody diagram again and look what is the friction factor for 6.8, so that's about 7, and now I need to reach here. So now I'm almost at 0.17, sorry. So now if I calculate my new velocity with f is equal to 0.017, which is roughly what I read in my diagram, I end up with velocity is equal to 6.76 meter per second, and that's pretty much converged at this point. You could do another iteration, but I think we can say safely that this is converged. So this is it. This is the way to calculate the flow rate when you do the pressure gradient, or the delta P or the delta H.